Thank you for coming along, ladies and gentlemen. So my name's Dr. Phil Dooley. By day I work out at the nuclear fusion experiment jet, but by night I do other weird stuff. My job during the day is to work with scientists. Although I did a PhD, I decided I wanted to be a communicator. I liked telling the stories a lot more. So now I tell stories for the scientists at JET. But one thing I've found as you try and tell a story is that the facts really get in the way. So I decided to take a different approach because the great storytellers of our culture, literature, religion, they're not constrained by facts. They make up all kinds of stuff all the time. And so I'm going to sort of loosen the facts a bit today and, tell some stories that excite, that entertain, that arouse your curiosity, that tell you what the human side perhaps is of what's going on with science. And, some of it will be factually accurate and some of it won't. For example, 50 Shades of Dark. Now, I'm not going to do 50. In fact, I haven't even read the book. I don't know much about it, except that Google told me it was the least popular Christmas present of 2012.
It's a book of dark matter, isn't it?
All right, so I'm first heckle for the night. Thank you. So let me tell you a little story about dark stuff, starting with astronomy and all the pictures of stars and things. Because the story of dark has actually been really important, and it's made a huge change to astronomy, to the way we view the whole world and how we view ourselves. Some would say it's a disaster, but scientists would say, no, it's really exciting, it's fascinating stuff. It all started with somebody thinking they knew it all, as so many of these stories. Simon Newcomb was a prominent American astronomer, and he was the founder of the American Astronomical Society, and he said, we are nearing the limit of all we can know about astronomy. How wrong he was. But let me explain why. What he was thinking about was light. And he's kind of right, because that's what we've been looking at. Now you people in Oxford may not recognise that. It's the sky. If you've been to a country like Australia where there's no clouds, then you would have seen something like that, but it still looks a bit unfamiliar because that's the entire sky pulled into one picture. So that's looking directly towards the middle of the galaxy and then sort of 180 degrees around. So at the edges there, you're looking directly away from the centre of the galaxy. And Simon Newcomb knew that the stars were so far away, they're unbelievably far away, even further than Scotland, that you cannot ever magnify them to any significant size. They're so small that no matter how strong your telescope, it'll still be a pinprick of light. So you can't find anything more about it. What he did about light, we realised that you can look at the colours, and that opened up a whole new world. But the dark side of things really opened up. Dark magic is very powerful, as we'll see during the night. So this story begins right in the middle of the galaxy, in Sagittarius. For those of you who are Sagittarians, you actually have a huge black hole in your heart. But if you look at Sagittarius, it looks more like a teapot, so really, what can you make of that? So when you look at this thing that to me always looks like a hamburger, right in the middle of it, right in the very middle of the galaxy, the astronomers were able to take a photo of the stars. Basically just blobs of light, that's all we can do. And then when they went back and photographed it the next year, and then the year after that, they found that these dots are moving. Now, as I said before, these are unbelievably far away. For them to move far enough for you to see it is extraordinary. They're moving really, really fast, close to the speed of light, moving huge distances in the course of just a few years. I mean, this is whizzing through from 1992 to 1998. So this was the first of the dark puzzles. What is going on? when you look at these very carefully, and you actually plot out the orbits of these stars, it turns out they're all orbiting around one single thing, one huge black hole in the heart of every Sagittarius, and that is what's making these things move around. And that's how we know that black holes exist. Not because we can see them, because they're black, but because of the effect they have on things around them. And now, that's 1998, so with another 14 years of data, you can actually plot out some quite amazing orbits, which I'll show you in just a little while. So, that's dark. That's a black hole in the middle of the galaxy. Now, when you start looking at how the rest of the galaxy rotates, then more of this dark problem unfolds. Because what you might think, if you look at that, is that there's lots of galaxy here, and it gets thinner and thinner the further out you go. Actually, there's hardly anything out here. And the physics of that tells you that this stuff would be going really fast, and this stuff is rotating very slowly. But when it's measured, that's completely wrong. It's actually the complete opposite. The things here are moving quite slowly, close in, except for the ones that are trying not to fall into the black hole. But around the outside, these stars are really cracking around. And again, it's completely wrong. What this tells us is that there's all this extra mass around the outside that's affecting the way that the galaxy rotates, that the stars around the outside are rotating. Now, an artist here has painted dark matter as blue. Obviously, it's not blue, it's invisible, it's dark. But what's amazing is to see that's the size of the galaxy, and look how much further out it extends, way beyond the edge of what we thought the galaxy was. We've measured this on the Milky Way, we've measured this on all sorts of galaxies around us, and we see that this is true again and again. There's all this extra stuff that we can't see. It's making things rotate way too fast. Now, it's got mass, because it does gravity, it attracts gravitationally, but we don't know what it is, it's dark, so why don't we call it dark matter? That's where the name came from, dark matter. So there's a number of explanations for it. Either it's a macho or it's a wimp. I kid you not, this is astronomers having a lot of fun making up names. The machos, massive compact halo objects. So they're saying there's planets, there's dead stars that are around the outside of this galaxy that have died out, stars that burned for only a few million years and now they're dead, and there's all this extra stuff. That was one idea, but it turns out from the way the measurements the astronomers have made, that actually doesn't hold. They've got to be little tiny particles. They're massive, meaning not massive, but massive in that they have mass. They're not like light, which has no mass. Photons have no mass, but these other particles must have some mass, enough that they're affecting how everything rotates. There must be absolutely trillions of them, and they must be everywhere. They must be around us here. There's actually dark matter all in this room, but because it's dark we can't see it. Now this all sounds a bit crazy, but there's more evidence. All of these, I mean, scientists generally are very skeptical, and they're the first people, if someone comes up with some crazy theory, oh, there's all this stuff that you can't see floating around, everyone will go, no, there's not, I can prove there isn't, la la la. So the only theories that get through are the ones that are absolutely bulletproof, that every scientist has had a shot at. So the way that they had a second sort of proof that dark matter existed came from Einstein's general theory of relativity, which says that light even is affected by gravity. So just as a meteor hits the Earth, or goes close to the Earth and will be attracted by the gravity of the Earth, even light, if the thing is big enough. So in this example, we've got a galaxy a long way away, a galaxy halfway in between us that's a really big one, a monster, and we're looking at it with these telescopes. So it looks Let me just rewind this video. I rated the ESO website, the European Southern Observatory website, heavily for this talk, so you guys should have a look at it as well. Alright, so when we look at our galaxy, it looks like that. It looks like basically a big white, and you can't see the red galaxy behind it because it's behind it. So as the light from this thing travels past the big galaxy, it gets bent around so that we end up still seeing it. What that looks like to us is a red smudge, or these funny circular smears around the outside of galaxies. So this is called gravitational lensing, and this has been observed again on lots of galaxies, enough for us to really think that this dark matter problem exists. Of course, if you've got too much matter, then that affects other things as well. Specifically, the life of the universe. Now the video won't go away. The Big Bang, you guys will remember, not because you're there, but because I'm sure you've heard of it. The Big Bang was a time when the universe was really small and all close together, very hot, and it began expanding. And now it's slowing down, we believe, and then it will come back in, or will it? This is the theory that is knocking around. We don't actually know what's going to happen, but I'd like to incorporate somebody's help to do the Big Bang for me. Any volunteers? Go on, good man. Okay, so the Big Bang was when it was very small. Stand up. Round of applause for Kevin.
I'm not even a scientist either. Am I going to do this right? Because I'm not a scientist.
Probably. Okay, so there's the Big Bang, and everything starts expanding. So you can see the things are expanding. And the question is, are they expanding fast enough that they will escape gravity? Or will gravity start to pull everything back in again? And so then the force will overcome the original expansion. So can you give up on the expansion and give us a bit of So that's called the big crunch, because that's telling us that the gravity of the particles of the whole universe will be enough that it all pulls in on itself and crunches back down into nothing. And that's called a closed universe, meaning that there's an end to the universe. The amount of time it takes to go up, then it will come down, and then all over.
I vote for that one.
Somebody wants an end to the universe. Patience.
Do you want your universe back?
I haven't finished with it yet. The other option is, of course, that it just keeps expanding forever.
Right.
Which is called an open universe. So then there's no time limit on the universe. It will just keep going forever and ever and ever. Until Kevin... That'll probably do. No. Not yet. Not yet. Okay, give us a big crunch again.
What? Crunch.
Yeah. There we go. There's the big crunch. That's the closed universe. So, thank you, Kevin. I'll need you again in a minute.
Weeks of training for that.
So the obvious thing to do is to look at galaxies far away and see how far they are, and how fast they're moving. I think my galaxies might have mostly rubbed off in the trip down here, but what you saw... I'm not going to go
It's tough, I tell you. That's why I did all the
Okay, give us a bit more, give us a bit more. What you will notice... Stand up there again. Face them. Come here. Can't get good help. You'll notice that these galaxies here that I've drawn on here, stay there, don't blow anymore.
Oh no, my stars have gone.
Okay, we need a galaxy. There's a couple of galaxies, another one over here. Pretty crazy shaped galaxy. Now, if this is our galaxy, as he blows a bit more, just a little bit more, you'll notice that the galaxy next to it doesn't move very far, does it? But the one over here, that actually moves quite a long way. So the key to us finding out how the galaxy, how the universe is expanding, is to look at galaxies that are on the other side of the universe, as far away as possible as we can see. Go on, let it go.
That's galaxy air.
Thank you. So what we have to do is look at faraway galaxies and try and get a handle on how fast they're moving. This seems incredibly difficult because it's hard to know how far the things are and therefore how bright they are and therefore how fast they're moving. It's really quite a complicated thing. Thankfully, we found this wonderful tool which is also happens to be, as physicists always like, the biggest explosion in the universe, apart from the Big Bang. This little star here, in 1987, was sitting there quietly. Then 2 weeks later, boom, it's that. It exploded in what's called a supernova. And a supernova, for a couple of weeks, gives out more light than all of the 10 billion stars in the rest of the galaxy. Suddenly, it goes absolutely crazy and explodes. The reason it does this usually is because, well, sometimes it's because it has a partner star around it and it's sucking stuff from its partner until it gets too much, reaches the critical mass at which a black hole forms, a critical mass at which space collapses on itself and becomes a black hole. It's a story you've heard too many times, haven't you? Stars who are sucking on all the people around them who then, collapse and... Okay, so turns out this is the only one we've ever seen in our galaxy. But looking at distant galaxies, we've actually been able to, in the 10 billion galaxies that we can see, each with 10 billion stars, there have been enough of them for us to get a real hang of how these things are moving. And so we can see now how these distant galaxies are moving away thanks to having what astronomers call a standard candle. We know exactly the same amount of energy is given out every time one of these stars blows up because it's got exactly the same, it's reached that critical mass at which it explodes. So that's really useful. So by looking at supernovas, we get an idea. So what did we find out? Is the universe slowing down and going to stop? Or is it going to slow down and do the big crunch? No. Another dark problem. This time, it turns out the galaxies are not going to come back in. They seem to be accelerating. That doesn't make sense because there's nothing there that can accelerate them. We've got gravity which is pulling them all back in. The Big Bang started it all off. Now they're all going to come back in. But they're actually being pushed apart by something. There's some pressure that's actually pushing the universe apart. We don't know what it is. We can't see it. So what should we call it? Dark energy. So not only do we have dark matter, which turns out to be about 5 times as much as we can see of real matter, but then we have dark energy, which turns out to be another 5 times again on top of all the matter. So it turns out now, no, I thought I deleted that. That's what we know, and that's what Simon Newcomb was saying. We know about, well, actually a small fraction of that is stars. There's a lot of gas and material in between galaxies. But that's only, about a fifth of all the matter, which is only a quarter of everything in the universe that we know. So this is a big problem. There's actually results today, which I tried to put in there and failed, from a satellite called Planck. The Planck telescope has been measuring the overall sky, the temperature of the overall sky, and that's actually adjusted these numbers. So it's more like 68% dark energy. So there's a little more dark matter than dark energy, but still, we're just as stuffed in terms of not knowing what is going on. No, not stuffed. It's exciting. Physicists are really. I mean, it is. It's the opening of a new epoch. Because when we hit a problem that's this puzzling, it means there's something big got to change. So there's one other thing that we need to talk about, which is what happens if the galaxies are being pushed further and further apart. You know it. It's your time.
Galaxy Man.
It's your time to shine.
Oh, you've heard of Coke Man. I'm Galaxy Man.
Okay, I'll never drink while you do this. So the galaxies are getting further and further apart. And they're getting faster and faster. Come on. And then eventually, the force of the energy is going to be so much that it blows the world apart. Thank you. Dark energy will first overcome gravity and the planets will fly apart, Earth will explode, then it will overcome the electromagnetic force and it will tear atoms apart. That's in about 10 billion years. But it's something to look forward to. That's called the Big Rip. So, with apologies to George, I'd like to sing a little song about this. Something in the way they move, attracted by some other body, something I can see so massive, I cannot believe my eyes, but data never lies. That something is a big black hole. Thank you. But I need some other body.